last lecture we introduced the operating system and traced its history with the different generations of computers. We also looked at the two basic concepts of operating systems, that is the file and the process. We saw inter-process communication and the problems associated with inter-process communication, that is mutual exclusion, synchronization and deadlock. Today we shall see the solutions that have been proposed over the years for these three problems. So, we will start with mutual exclusion. Now, basically we saw that mutual exclusion has to be provided by not allowing processes to enter their critical sections at the same time, because it is in the critical sections that the process accesses its shared resource. So, and when it comes to a critical section, it is also always preceded by interrupts. So, the simplest solution that occurs to mind is to disable those interrupts. In fact, that is the first solution that we shall see, disabling interrupts. So, let the user process disable all CPU interrupts before entering its critical section, and once it is done with the critical section, it can enable all the interrupts after leaving. This prevents the other processes from being scheduled, and once they are not scheduled, they cannot enter their critical section. So, only one process is in its critical section at the same time. Now, this is a good solution, it is a simple solution, but it has a major disadvantage, and that disadvantage is that we are giving to the user process the power to turn off interrupts. This is all right, except that the process may be a malfunctioning or a malicious process, in which case it may like to hog the whole processor at the same time, and therefore it may turn off the interrupts and never turn them on again. This is a major disadvantage, and this has to be, so this kind of solution, disabling interrupts, does not work. The other solution that was proposed earlier is to have a variable called a lock variable. In this case, we have a single shared variable which is called the lock, whose value is initially set to 0. So, whenever the process wants to enter its critical section, it first tests the value of this lock. If the value is 0, it sets it to 1 and enters the critical section. Else, if the value is 1, which means that some other process is already in its critical section, then this particular process will have to wait until the lock becomes 0 again. This means that each process gets its own turn to enter the critical section. It can enter its critical section only when the lock is 0 and by setting it to 1. Now, this solution is also fairly simple. It is a software solution as opposed to the hardware solution provided by disabling interrupts. But this also has a major disadvantage, because if after testing for a 0 and before the value of the lock can be set to 1, another process is scheduled on the processor. That process will also test the value of lock, it will find it to be 0, it will set it to 1 and enter its critical section. So, we shall have the unwanted scenario of two processes entering the critical section. This happens because the testing and the incrementing of the value are two different operations, and any process can be descheduled between those two different steps. The third solution that was proposed is what is called strict alternation. So, we have an integer variable called turn, whose value is 0 initially, and this keeps track of whose turn it is to enter the critical section. The first process, let us say P0 or P0, inspects the value of turn, finds it to be 0 and enters its critical section. Now, if P1 is scheduled and it wants to enter its critical section, it will find that the value of turn is 0. So, it must wait till the value of turn becomes 1, because the value of turn equal to 1 means that it can enter its critical section. This is a strict alternation mechanism where the basic disadvantage is that no process can enter its critical section twice in succession. So, it is not really a very good solution because there is strict alternation and every process has to wait for its own turn to enter the critical section. Also, all the three solutions that we have seen, that is the disabling interrupts, the lock variable and the strict alternation, these are what we call busy waiting solutions, which means that the CPU wastes its time whenever a process waits in a loop continuously testing the value of turn. Only when the turn value becomes equal to the value given to the process does the process enter its critical section. So, the time of the CPU is lost waiting for the value to turn from 0 to 1, from 1 to 2, etc. These are all therefore busy waiting solutions. A fourth solution that is proposed is like the lock variable, except that this is a hardware solution rather than a software solution. This solution uses the TSL instruction, which is the test and set lock instruction. Using this hardware instruction, which is an indivisible instruction or an atomic operation, which means that the testing and the locking and the setting is one single atomic operation, and no process can be descheduled from the processor in between these two steps. So, only one process can test and set lock in one single go. Using a shared variable like flag or lock which is equal to 0, this can be set using TCL or TSL by any process to the value 1 and without any intervention from any other process. So, this TCL instruction, use of this instruction is a hardware solution which is better than the lock solution, which is a software solution. But again, this has the disadvantage that it makes the CPU waste time because it is a busy wait solution. So, we want to look for a solution where the CPU does not have to waste time busy for a process which is waiting. And for this we have the fifth solution, which is the use of primitives. A primitive is a basic instruction, the simplest instruction at the hardware level, and sleep and wake up are two such primitives that we shall use in this solution. So, let a process block rather than waste CPU time if it is not allowed to enter its critical section. The process will therefore not wait in a cycle, it will simply block and let some other process run. There will be two primitives, the sleep primitive, which is a system call to block the caller process, and the wake up P or wake up process primitive, which is a system call to wake up the process P. Let us see the use of these two primitives in a classical operating system problem, which is known as the producer consumer problem. The producer consumer problem states that there are two processes, the consumer process and the producer process. They share a common fixed sized buffer. The producer puts information into the buffer and the consumer takes it out. So, things go normally, the producer produces information, puts it into the buffer, the consumer takes it out and consumes that information. But the problem arises when the buffer is full. This is a problem for the producer because the producer cannot put any more information in the buffer since it is full. And for the consumer, the problem arises or the trouble arises when the buffer is empty, because it cannot take out any information from an empty buffer. So, both must sleep till one removes from or puts into the buffer and wakes the other up. So, let us see a simple code which takes care of these two processes. this is a code which will have a problem. So, we are calling it code with race, and then we shall try to remove this race problem and have a solution without race. So, the on the monitor we have the code, we have include prototypes, the normal including primitives or commands. Then we define a buffer of size 100, n is equal to capital N equal to 100. We have a variable integer variable count which has an initial value 0, and the consumer process starts here, the consumer, which continues in a loop. So, while true, it tests the value of count. If the value of count is 0, then it goes to sleep. We shall discuss this particular asterisk which provides the whole problem later. So, the consumer simply counts, checks the value of count. If it is 0, it sleeps. Otherwise, if it is not 0, that means there is an item in the buffer. So, it removes that item, decrements the count, count becomes count minus 1, and if the count is n minus 1, it wakes up the producer. The producer, which means that if since the value of was initially n, the producer must have gone to sleep. So, the consumer removes the item and consumes it. Let us look at the producer. The producer also works in a loop. It produces the item, and if the count is n, it sleeps. That means the buffer is full, so it goes to sleep. It enters the item into the buffer, increments the buffer, the count to by 1, and if the count is 1, which means earlier if the count was 0, then the consumer would be sleeping. Therefore, it increments the value of count. If the value of count is 1, it wakes up the consumer. So, this is the basic code. It is a simple code using the sleep and wake up primitives. But this code, as I said earlier, has a race. It is not a true solution because something is wrong with this code. Now, let us see what that is. Let us say at this point where I have put the asterisk, that means after testing the value of count to be 0 and before it can sleep, the consumer is taken off the process. So, that means consider that at this point C is descheduled or taken off the processor before it goes to sleep. So, at this point where the asterisk has been put. Now, therefore, when it goes when it counts and it is taken off the processor, the other process, that is the producer, will run and it will put an item in the buffer. It will increment the buffer, so count will become 1, and then it will do a wake up to the consumer. But the problem is that the consumer has not gone to sleep yet. It has still to execute the sleep primitive. Therefore, the wake up to the consumer is lost. The consumer will then, because the producer goes to sleep after waking up the consumer will now come on the processor and immediately it will go to sleep. The producer will run again and it will continue running and eventually put 1, 2, 3, 4 n items into the buffer and go to sleep. So, at this point both the producer and the consumer are asleep, and this is a situation which is called deadlock. So, this is the problem with this particular code. It is possible if the situation arises that the consumer goes to sleep or it is descheduled from the processor at a particular time, both of the processes will sleep and nothing can run on the processor. This is the situation which is called deadlock. Basically, the problem has occurred because the wake up sent to a process which is not yet asleep is lost. So what is the solution? How do we avoid race from this producer consumer problem? It should be noted that the producer consumer is a major or an important problem which is used to test the efficacy of a solution for providing solutions to the IPC problems whenever a new primitive is designed. And therefore, we shall discuss how some other solutions will work for the producer consumer problem. And that is when we arrive at the semaphore. The semaphore is an important milestone in the eventual discovery or development of the operating system, because all operating systems now use semaphores. The semaphore was suggested by Dijkstra in 1965. I have already mentioned earlier that Dijkstra is considered the father of operating systems. Dijkstra suggested the semaphore, which is basically a low level non-negative integer type. It was first implemented in the ALGOL 68 language, and it has two atomic operations associated with it, the down operation and the up operation. So, we have down semaphore or PS and we have up semaphore or VS. In these two operations, we have the down semaphore, which simply checks if the value of the semaphore is greater than 0. If it is, then it decrements the value, else it puts itself to sleep. The up semaphore or VS simply increments the value of the semaphore. Now, up and down are implemented as system calls with interrupts disabled. This is important because the interrupts are disabled, so nothing can happen in between. For example, between checking and decrementing, no operation can take place, and since the interrupts are disabled. These interrupts are, this is the very basic operation, so the interrupts are disabled for a very short time, so it does not harm the working of the system. So, semaphores are of two types. We have binary semaphores, which are used to provide solutions for mutual exclusion, and we have counting semaphores, which are used for synchronization. Now, let us see a solution to the producer consumer problem using these semaphores. So, on the monitor we have the same value n, which defines the size of the buffer as 100, and we define three semaphores: semaphore mutex, which is a mutual exclusion of semaphore, or binary semaphore, which has a value 0 or 1 and its initial value is 1. We have the semaphores called empty and full. These are synchronizing semaphores whose values, or counting semaphores, and their value can go from 0 to n. Initially the value of the semaphore empty is n and the value of the semaphore full is 0. So, the producer, the code for the producer looks like this. We have the integer item and the producer goes in a loop. While true, it produces the item and then it does a down on the semaphore empty, it does a down on the semaphore mutex, which means that since the value of empty was initially n, which means that n buffers are empty. That means all n slots in the buffer are empty. So, the value of empty is 100. So, the down is successful. It does a down on empty, that means the value of empty now becomes n minus 1. It does a down on mutex, mutex was initially 1. So, it becomes 0 and it can now enter an item. So, it enters its critical section and puts an item into the buffer. So, enter item, this part of the code happens to be the critical section for the producer. where it is accessing the shared buffer. Notice that the critical section part of the code is covered by these semaphores, down mutex and up mutex. So basically what is happening is that the producer is decrementing the value of mutex to 0, entering its critical section, and when it leaves the critical section it is incrementing the value of mutex, which means that when or while the producer is inside its critical section, the consumer cannot enter its own critical section. Let us see why it cannot do that, when we will see that when we see the code for consumer. So once it comes out of the critical section, the producer will up or increment the value of mutex. It will also up the value of full. Now let us look at the consumer. The code for the consumer looks like this. While true, the consumer first downs full. Full indicates that the buffer is full, and therefore the consumer must decrement its value so that it can take an item from that buffer. It must enter its critical section to remove that item. The critical section of the consumer consists of that single statement, remove item, and this is also guarded by the down mutex and the up mutex. So the consumer can enter its critical section only when it is able to down mutex. That means the down on the mutex is successful. If the value of the mutex is 0, then the consumer cannot down mutex. We say that the down on mutex has failed. So only when the down on mutex succeeds does the consumer able to enter its critical section and remove an item. So it does that, removes the item, ups mutex, which means that it increases the value of mutex. It ups empty. So it simply means that now empty, there is one empty. Earlier there was no empty. Now when value of empty becomes 1, it consumes the item, and this is the loop that it gets into. So these are the two processes for the producer and the consumer. If we study these two processes and their code, we will find that there is no place in these code where anything can go wrong. The values of the initial values of the 3 semaphores make it, or they ensure that the two processes cannot enter their critical section at the same time, and therefore the solution that we have proposed for the producer consumer problem using these semaphores is a correct solution, and does not have either race or deadlock. It also does not have starvation. We can check that by trying various combinations of the producer running or the consumer running, and we will still find that there is no problem at all with this solution. So does that mean that the semaphore is a very good solution and that no other solutions are necessary? That is not correct. There is a basic simple flaw with the use of semaphores. The disadvantage with the semaphore is that in a complex situation there may be many semaphores. Here in this case we used only 3 semaphores. So lining them up, when to do a down on the semaphore, when to do an up on the semaphore is fairly easy. But if it is a more complex problem and we are trying to solve it using semaphores, then it might happen that we do not line up the semaphores and their operations correctly, in which case there will be problems. This simple flaw can be shown with the producer consumer problem also by simply exchanging in the code for the producer. If we simply exchange the two statements down mutex and down empty. So we first do a down mutex and then we do a down empty. instead of the other way around. It will be seen that this solution will not work and it will lead to deadlock. What I am saying is that if mutex is decremented before empty is decremented instead of after it, then if there is a situation when the buffers are full, then the producer will block with the mutex equal to 0, and the next time when the consumer tries to access the buffer and tries to do a down on mutex, the value of mutex is already 0, so the consumer will also block, and both the processes will stay blocked forever and no work will be done. That means the deadlock situation will arise. So this is a simple flaw which has occurred because we have unknowingly or unwittingly exchanged the two downs on the mutex and empty. So which tells us basically that we should be very careful in using semaphores. If we make the smallest error, then all the work is halted. So that is the use of the semaphore. In fact, the semaphore has been used to solve many other what are called classical IPC problems. Another problem that we have is the problem of the readers writers, and we have the problem of the dining philosophers. These two problems will be discussed a little later along the course. Right now we shall look at another very useful solution for solving the problem of IPC or inter-process communication, and this is a problem which is called the this is a solution which is called the monitors. The monitors were proposed jointly by C.S. Hoare in 1974 and P.B. Hansen in 1975 along the same time. This monitor is a higher level synchronization primitive, and it was used earlier only in concurrent Pascal, Pascal plus, concurrent Euclid, modular 2 and 3. The monitor is basically an abstract data type. In fact, it is like a language construct. It is part of the language rather than being part of the operating system. Lately, the Java language has monitors associated with it. The monitor is a collection of procedures, variables and data structures all grouped together in a special kind of module or package. The way the monitor is used is like this. Processes can call monitors, but they cannot access the monitor's internal data structures from procedures which are declared outside the monitor. And monitors are basically used for synchronizing processes. They are also used for solving the problem of mutual exclusion. This is done automatically, unlike in semaphores where semaphores have to be programmed to provide mutual exclusion. The monitor, because of the way it is built, it automatically provides for mutual exclusion, because only one process can be active inside a monitor at any instant of time. Now this will be clear by taking a example of a monitor. We shall see the basic framework for a monitor. The monitor is a software solution where we have certain integers, certain data structures or variables associated with it, and we have for example in the producer consumer problem, we will have the procedure producer and we will have the procedure consumer, and we will initialize the variables and then the monitor will start running. So we said that the monitor is a programming language construct. It has a built-in compiler which treats the monitor call as a separate entity from a normal procedure. When any process calls the monitor procedure, the first few instructions of the procedure will check to find if any other process is already in the monitor. If so, the caller process will be suspended until the other process, which is already inside, leaves it. If there is no other process inside the monitor, this new process will be allowed inside. So, the simple way to use the monitor in order to provide mutual exclusion, that means in order to ensure that no two processes are in their critical sections at the same time, is to turn all critical sections into monitor procedures, so that no two processes will execute their critical sections simultaneously. Implementation of concurrent processes using monitors is easier and safer because of the built-in compiling operation. So, it leaves the user or the programmer with less chances of going wrong. But how do we block the process? We have not seen any blocking variable yet. We have seen only the integer variables. That is where we come to the condition variables. If you recall, we had the condition variable inside the monitor. So, this condition variable will be used to block a process from entering the or calling the monitor procedure. Like a semaphore, there are two operations on the condition variable. There is a wait operation, which basically delays or blocks the calling process, and the signal operation, which wakes up or continues the process. The basic advantage with monitors is that it cannot happen that while one process is trying to sleep, another is trying to wake it up. This is ensured by automatically provided mutual exclusion on the monitor procedures. We have already said that since the compiler implements mutual exclusion in monitor, the errors are unlikely, unlike what we had in semaphores. And this implementation of the mutual exclusion is transparent to the processes. All that the programmer has to do is to turn all critical sections into monitor procedures. So, this may sound a little confusing, but we shall now see an example of the producer consumer problem solution using monitors. We declare a monitor called producer consumer. We use two condition variables, full and empty. These are the analogous to the full and empty semaphores that we used in the semaphore solution. We have the same integer variable count, and we have two procedures in the monitor for the producer consumer. The first procedure is the enter. Now, recall that the enter will be the procedure where the producer will enter data into the buffer. So, this is the part where it will access the shared buffer, and hence this part will be the critical section, and this critical section we have put inside the procedure enter, which is simply says that if the count is n, then wait. The producer has to wait because all the buffers are full. It waits on the condition full, else it enters the item, increments the count value, and if the count is 1, then it signals empty. It signals empty, saying that now empty has become 1. Similarly, we have a procedure remove, which will be called by the consumer, and this is the critical section for the consumer. The same thing is done here. If the count is 0, that means there are no empty, no full, that means the buffer is full, then it has to wait on empty. The value of empty is 0. So, it waits on empty, otherwise it removes the item, decrements the count by 1, and if the count is n minus 1, that means there is one single buffer empty, then it signals full, that means the value of full is incremented So this is the procedure remove. The last part of the monitor is where we initialize the count variable, and the count variable is initialized to 0, and this is the end of the monitor. Now the process producer will therefore look like this. We simply say while true, do begin, produce item, and producer consumer dot enter. That means call the procedure enter. That is all that the programmer has to do, is to write a loop in which the producer produces the item and calls the monitor procedure enter. That means producer consumer dot enter. Similarly, the consumer process is simple. We have the consumer call the monitor process or monitor procedure remove by doing a producer consumer dot remove, removes that item and consumes it. So the task of the programmer has become simpler. He or she does not have to bother about lining up the semaphores properly. All that is done by the monitor automatically. The monitor procedures enter and remove ensure that the mutual exclusion problem is solved, the deadlock problem is solved, and the producer is synchronized with the consumer. So what we are saying is that the basic advantage of the monitor is that it makes parallel programming less error prone than it is with semaphores. Of course, it has a disadvantage. The monitor as a language is a language construct, and therefore we have seen that it is not implemented in C and C++. Hence the compiler cannot enforce mutual exclusion. What we are saying is that the monitor is not implemented in C and C++. I said earlier that it is now being implemented in Java. Of course, these languages do not have semaphores either, but semaphores are easy to implement by the programmer. Another disadvantage of the monitor is that it has been designed like the semaphores for providing mutual exclusion on CPUs which have shared memory. So if it is a multi-computer system or a multi-processor system which has shared memory, then it can be used, and the same disadvantage is there for semaphores also. Some monitors do not allow nesting, and some allow nesting. If nesting is allowed, deadlocks can happen. So all in all, what we are saying is that with semaphores there is a problem that they are too low level. With monitors there is the problem that they are unusable because they are in most languages, because they are not implemented in that language, and therefore we need a third solution. And the third and most likely most popular solution to solving the problem of inter-process communication with systems that do not share memory is the message passing. Message passing using what is called the remote procedure call, or RPC. The remote procedure call, the messages are sent from one process to another, and the message traffic takes the form of a request message from the client to the server. So basically we are talking of client server technology. Message passing is implemented with CS or client server terminology. The message goes from the client to a server, which is a request message, and there are reply messages from the server back to the client. These can be implemented very much like calling procedures. So here what I have shown is the client and the server, and there are 6 messages that are traveling between the client and the server. So the client is here, the server is here, and they do not have this is one machine, the client machine, this is a remote machine which is a server machine, and they do not have any shared memory with them. This is the network through which the client is connected to the server. The client does not talk directly with the server, it has a stub. Similarly, the server has a stub which does the actual talking. So, whenever the client wants some service from the server, the client and server are remote processes. These are both processes which are remote on remote machines connected through a network. The client simply calls a procedure on the stub, that is 1. 1 is a procedure call. The stub will then send that message over the network to the server stub. So, 2 is the actual message, 2 and 5 are messages. When the stub receives the message, it will locally call the server. This is a procedure call again. The server will provide the service. For example, the client might want to know what is the time of the day. So, it sends a time of the day request to its own stub. It does not know where the service occurs or where the server resides. It simply says to its own stub to send the time of the day. The stub knows that the time of the day server is on a remote machine. So, it sends the message number 2 to it, which is received by the server stub. The server stub does a simple local procedure call to the server. The server will answer or service the request and send a return procedure. Through a return procedure, it will send the time of the day to the stub. The stub will reply a message, 5 is a message, to the client stub, and then the client stub will in return do a procedure return and give the value of the time of the day to the client. This is how the message passing occurs. This is how the client process and the server process communicate with each other using message passing, which is a mechanism which is transparent to both of them, because they are not aware that they are on a different machine altogether. So, message passing uses two primitives, send and receive, which like semaphores, but unlike monitors, are system calls. They are not language constructs and can easily be put into library procedures. The send and the receive are parameterized. The send has a destination parameter and a message parameter. Similarly, the receive has a source parameter and a message parameter. So, the sender is basically sending to a destination a message, and the receiver is receiving from a source a message. So, this is how they communicate, and if the receiver is not ready to receive a message, the sender could block, and if the receiver is waiting for a message, but the message does not arrive, then the receiver could block. So, that is the send and receive primitives, which are used to provide inter-process communication between remote processes. That means processes which do not share memory. So, here we have a solution which provides the answer to the inter-process communication problem on systems or processes which are remote to each other, which do not share memory. But if the two machines are heterogeneous, then what happens? That is a problem with message passing. So, if we have a Linux machine, a machine with an operating system Linux on one and Windows on the other, they may not be compatible. And what is called the failure semantics is also an important aspect of message passing. Messages can be failed to be sent or received, in which case they have to be resent, or a duplicate message has to be sent, or a duplicate receive has to be done. So, when such a failure occurs, what should be the failure semantics? Should the message be sent at least once, or should it be sent at most once, or should it be sent as a maybe? Either it is sent or it is not sent, there is no guarantee, but of course, this is the easiest semantics. So, the design issues that are connected with the message passing are that it is challenging, especially if the two processes are on different machines and the system is heterogeneous. And because they are on different machines and they are connected through a communication channel, that channel can be error prone. Error prone channels means that the message could be lost, which means that it does not reach its destination. The message could be garbled, which means that it got corrupted on the way because of interference in the channel, or for whatever reason it did not reach the destination, in which case the receiver will have to ask for a duplicate, and the sender will have to send duplicate messages. And this gives rise to what are called acknowledgements. The receiver must acknowledge the receipt of a message. He must request for sending duplicate messages, etc. So there are a lot of issues, design issues associated with message passing mechanisms. Another major issue is how to name processes. So if I want to send to, if I am process A and I want to send to process B, then I must have a name, the other process must have a name. When they are on the same machine, also this arises. The issue becomes more critical if the processes are on different machines which are connected through a communication channel. So naming of processes becomes important. It becomes a major design issue. Naming should be unique. No two processes should have identical names, etc. And the other aspect has to do with security, which means all the processes must be authenticated. There should be no malicious processes which may enter the system and try to corrupt the system. So authentication is a major issue. How do we authenticate messages, processes and their messages? Also another major disadvantage with message passing is that because the processes are on different systems, on different machines, so to sending a message which is basically a copy operation from one machine to the other takes much more time. So message passing is a slower mechanism than a semaphore operation or entering the entering the monitor. So next time we shall see the producer consumer problem and see a solution with message passing. So now we look at the solution to the producer consumer problem using message passing. Here we, on the monitor, we see the same buffer, n is equal to 100, that means the number of slots in the buffer. We have the message size and we have the producer. The producer produces the item, that means it generates something to put in the buffer. Now it receives from the consumer an empty packet to arrive. It builds the message, that means it constructs a message to send and sends to the consumer the message. So we are using the send primitive to send to the consumer. The consumer on the other hand continuously, for I is equal to 0, I less than n, it continuously till I becomes positive, it sends to the producer n empty packets, and while true it receives from the producer the message, extracts the item and sends another empty to the producer, and it then consumes the item. Now notice here that there is no question of any mutual exclusion because there is no shared memory. So the problem of mutual exclusion does not arise in this particular solution. We only need to synchronize the producer and the consumer, and that we have done by using the two primitives send and receive. The only difference between this solution and the earlier solutions is that we want to limit the number of packets in the system, and therefore we require the consumer to send these n empty packets to the producer. Every time the producer gets an empty packet, it can fill in that packet and send the message to the consumer. the consumer can extract the item, consume the item, and then send back another empty to the producer. So, this is the solution of the producer consumer problem using message passing. And we have seen that there are no problems in this solution. The concept of mutual exclusion does not arise because they are not sharing memory, and this provides for a complete solution on heterogeneous when the producer and the consumer are on different machines. In the next chapter, we shall see processes and how they are implemented, and we shall see scheduling of processes. Thank you.